I'm going to continue looking at high-throughput characterization of mechanical properties by looking at a class of techniques called indentation methods. We're going to look at some examples of high-throughput characterization using indentation methods and some applications in polymers and coatings. So in an indentation test, an indenter moves down, touches a sample, and pushes into it. It deforms the sample, and force on the indenter is measured as a function of distance. Now the indenters can be nanoscale, microscale, or even macroscale. Usually the force versus distance has to be converted into stress versus strain, and this allows extraction of parameters like modulus, strength, or toughness. Now, in addition to having the indenter move normal and push into the substrate, you can also have the indenter load the substrate and then move parallel to the substrate like this. In this configuration, you can measure properties like scratch resistance and friction. So one of the examples I'll talk about is using a nanoscale indenter testing instrument called a nano indenter. This is actually the 24 by 24 array of diacrylate polymers that was examined by these authors, Tweedy and coworkers in Advanced Materials. Now we've looked at this library before, and the reason I keep coming back to it is because these authors wrote a series of papers where they described how different types of properties could be assayed on this type of microarrayed library. So this is actually one of the tiniest sample libraries known, where the spots of polymers were actually only 300 microns, 0.3 millimeters in diameter. So this is a relatively challenging system, miniaturized, to do mechanical property measurement. So what the authors used was an instrument called a nano indenter that essentially has a nanoscale diamond tip probe that pushes into known positions on the sample and is automated, can go from point to point on your sample. So the data looks something like this. You measure load, the measured load or stress on the tip versus depth. And the dart curve, for example, shows the indentation and then the withdrawal as a function of depth for a relatively stiff material. The dashed and dotted curves are progressively softer materials. So one can use mechanical models that take into account the geometry and extract information like the modulus. So here for example, is the modulus with error bars measured on the 24 by 24 member library of combinations of two monomers. So a very large amount of data that can be collected here on one library. It can be collected in triplicate because on their single microscope slide they had 3 of these libraries made in triplicate. And you can see a really wide range of mechanical property modulus values was produced. So I'd like to talk about another example. This one is from my own work at the other size scale. This is an indentation test that uses a 0.5 millimeter, a relatively large indenter, 500 microns. The indenter can be seen here in the inset image. It's actually a steel pin that has been machined on its head to have a hemispherical cap. This is moved by a linear motion stage up and down. And then the bottom, on the bottom you can see the mechanical isolation mount. This is essentially 2 steel plates that have holes in between in the plates, and you would sandwich a sample. It could be a polymer, it could be a ceramic or a metal or a composite, and each hole would then become an individual isolated sample area. You can see the blue 2-stage, 2-axis motion system. This would position the sample underneath the needle, the pin, and the pin can contact the sample at various speeds, going from very slow static measurement up to impact speeds. And it can even puncture the sample and measure failure properties. Here's another shot looking from the side of the instrument. So this is actually inverted, but it gives you an idea of what happens when the indenter touches a sample. The original sample film, this is a cross-section of the circular measurement hole the original film is under the dotted position, it would be deformed, and the film would be stretched around the tip as it pushes into the film, and you would have a force on the tip, F of Z, that would be measured. And using the geometry, you can convert this force to stress, and you can convert the film stretched length to a strain. So some of the data looks like this. This is raw force versus time, where force is on the vertical axis and time on the horizontal. The original signal has some noise in it. That's due to vibrations in the apparatus. But you see the sample gets loaded, and you see an increase in force. There's a little bit of yielding, so it goes through a maximum, and then all of a sudden, it snaps the film. That's where the film breaks, and it goes back to zero, and there's some vibration due to the actual the vibrational noise when the sample snaps. This can be readily denoised and removed automatically, and the filtered signal, you can get information like tensile strength, the toughness, the Young's modulus, and the strain at break, all from this one measurement. Here's an example of some of the capabilities. This is a single nylon 6 film. We've impacted at high speeds here, 16 independent positions. This gives you an idea of the details that you can see. This is exactly what we would expect from a nylon. You see a yielding behavior, which is the first little maximum, and then you see a strain crystallization, which means the stress increases as you continue to strain it. And finally, the material breaks at around 60% strain. But the error bars here give you an idea of the point-to-point repeatability, which is quite good. Here's an example of an application. We're comparing here the uniaxial modulus measured in a conventional instrument to the biaxial modulus measured on the high-throughput mechanical instrument. For polyurethane ureas, you can see that there's a strong linear correlation that can actually be predicted by theory between the uniaxial, the normal measurement people usually use, and the new high-throughput mechanical measurement. And we're actually going from a ductile failure mode to a brittle failure mode as we change the composition of the urethane urea material. Here's another example. I talked earlier in the lesson on electronic properties about these proton exchange membranes. These were the conductivities we measured. But if we can take this library after we measure conductivity, and we can then measure the mechanical properties at the same positions. And so for the Kynar 500 row, for example, these are the mechanical properties we measured as a function of polyelectrolyte content. So now we have a map of both the conductivity as well as the mechanical properties on this one sample. So that finishes my look at indentation testing. Next, we're going to look at abrasion and buckling type tests. Thank you.